To a human, this is a spreadsheet. It's a list of students, how long they studied, and what they scored. But to a computer, this isn't a list, it's geometry. To a computer, predicting a test score isn't about learning. It's about finding the best possible solution to a system of linear equations that is fundamentally unsolvable. In this video, we are going to decode linear regression. We will bridge the gap between the math we see in textbooks and the code we write in production. We will solve the geometry, build the algorithm from scratch in Python, and finally discover the deep probabilistic reason on why it works. Welcome to Decoding Complexities. I'm Pradeep. Let's translate this into the language of linear algebra. Spreadsheets are great for storing data, but they are terrible for computation. If we want to manipulate a million data points at once, we need a matrix. We take our input features like the number of hours studied and organize them into the design matrix, denoted by a capital X. Every row is one student and every column is a feature. Next, we take the answers, the actual exam scores, and form a column vector. We call this the target vector Y. And finally, our model is simply a set of weights. We want to multiply the number of hours studied by some weight W to get the score. We want to solve the equation xw equals y. But there is one catch. Real-world data needs a baseline. Even if you study for 0 hours, you probably won't score a 0. We need an intercept. To handle this, we use a standard linear algebra trick. We add a bias column of 1s to our matrix X. In the real world, we have more data points than features. This makes our system overdetermined. It is full of contradictions. Geometrically, the target vector Y does not live in the column space of X. The system is unsolvable. So, we need to find the best possible compromise. We need to find the weights W that minimize the error. Think about a shadow. The error is the distance between the real target and our prediction. To minimize this error, we want the shortest possible distance. Geometrically, the shortest path from a point to a surface is a line that goes straight down, perpendicular to the surface. If the error line was slanted, we could slide our prediction over and make the error shorter. Therefore, the optimal error must be orthogonal to our data. Mathematically, this means their dot product is 0. This single geometric fact, x transpose times error equals 0, gives us the answer key. From this, we derive the famous normal equation. X transpose multiplied with y minus xw equals 0. This gives us the equation x transpose xw equals x transpose y. We can then solve it like w equals x transpose x inverse multiplied with x transpose y. And this equation gives us a direct analytical way to calculate the best fit line. Let's get started with the code. We will implement this using NumPy. First, let's define our raw data. Before we solve, we must handle that intercept. We augment our feature matrix by stacking a column of 1s next to our raw data. Now, we construct the normal equations. We calculate the left-hand side, x transpose x, and the right-hand side, x transpose y. Now, we have a solvable system. To find the weights, the math says we need to invert the matrix. But here is the thing. In production code, we always avoid calculating the inverse explicitly. It is computationally expensive and numerically unstable. Instead, we use a solver method, which is NumPy's linear algebra solve, which uses a smarter, faster algorithm to find the answer without breaking the math. The output gives us our model. The baseline score is 32.79 and the bias is 10.05, which means every hour of studying adds about 10 points roughly. But a model is useless if we don't use it. Let's predict the score for a student who studied 0 hours. We construct our input vector, remembering the bias term, and simply multiply. It works perfectly. And visually, the line cuts right through the center of our data. Our geometry worked. We minimized the squared error, but why squares? Why not absolute difference? Is it just because the math is easier? It turns out there is a deeper reason. Let's assume the noise in our real-world data follows a Gaussian distribution, a bell curve. This means any data point is just a random sample drawn from a normal distribution centered on our line. We want to find the specific line that makes our observed data most probable. This is called maximum likelihood estimation. If we write out the probability formula for a Gaussian and try to maximize it, the math simplifies in a shocking way. Maximizing the likelihood is mathematically identical to minimizing the squared error. This is the profound insight. If we assume your data has Gaussian noise, then least squares isn't just a geometric trick. It is the statistically optimal way to solve the problem. So we have the complete picture. We used geometry to derive the solution, code to implement it efficiently, and probability to prove why it's correct. But there is a flaw in what we just did. We trained our model on all the data we had. We used every single data point to find our line. How do we know if this model works on new students? Or did it just memorize the answers we gave it? This leads us to the concept of overfitting and the train-test split, which is the foundation of practical machine learning. If this deep dive was valuable, check out the companion blog post and the Google Colab notebook linked in the description to run this code for yourself. Hit that like button and be sure to subscribe, because in our next video, we will tackle the biggest danger in machine learning, overfitting, and how to solve it with the train-test split. Thank you for watching, and I will see you in the next one.